day, grade 12 learners. Welcome to today's physical science lesson. My name is Mashudu Mamboro. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Today we'll be focusing on a topic, chemical change, which now the knowledge area is chemical change. The topic is acids and bases. So we'll be focusing on acids and bases. I know that you have started this topic in grade 11. So we'll first look at that, your prior knowledge and all that. So at the end of this lesson, we are saying you must be able to know how to define an acid and a base according to Arenas and Lorentz. So acids, you must know how to define an acid and a base according to Arenas and according to Lorentz theories. And according to Arenas theory, is saying that an acid produce hydrogen ion. So I want you to look at it that way, to say an acid produce. So you define an acid by what it produces. It produces hydrogen ion in aqueous solution. It produces hydrogen ion in aqueous solution. So that's all we're expecting you to do, to say an acid produces hydrogen ion in aqueous solution. So how many ways? 1, 2, 3, 4, 5. That's 5. So you are able to say, when I define the acid, I will say what it produces. It produces hydrogen ion. You can just write the hydrogen ion is H+, hydrogen ion in aqueous solution. So an acid produces hydrogen ion in aqueous solution. Whereas a base, according to Arenas, it produces hydroxide ion. You can write hydroxide ion as OH- in aqueous solution. So I'm simply saying those 5 ways are enough to say a base produce hydroxide ion OH- in aqueous solution, whereas an acid produce H+ in aqueous solution. But however, if you want to write the hydrogen ion in full, you can write it in full as hydrogen ion, or you can write a hydronium ion H3+, or you can write hydronium ion in full. But any of those, you will get your 2 marks. So just know that acids, we are saying you produce them, you define them according to what they produce. So we're saying an acid will produce hydrogen ion in aqueous solution, a base will produce hydroxide ion in aqueous solution. Now, according to Lorentz, we're saying an acid is a proton donor, a base is a proton acceptor. So an acid is a proton donor and a base is a proton acceptor. Definitely, you cannot go to your exam without knowing these definitions. Is the first thing. You can't do acids and bases without knowing what acids and bases are. So it's important that you know that you can define acids and bases according to Arenas theory and according to Lorentz. Arenas said an acid is a produce hydrogen ion in aqueous solution, whereas a base produce hydroxide ion in aqueous solution. Lorentz, an acid is a proton donor, a base is a proton acceptor. I hope you have that. You will remember that at all times. Now, the other thing that we must focus on is to be able to distinguish, to differentiate between strong acids, strong base, weak acids, and weak bases. When do we say the acid is strong? So we're talking about the strength of an acid here. Say, when we say the acid is strong, is when the acid can ionize completely in water. So when you put the acid in water, it ionizes completely to form high concentration of hydronium ion. So what are we saying? We're saying if you are having, for example, HCl, when you put HCl in water, it will completely ionize. It will completely ionize to hydronium ion and Cl- like that. So when you say it ionizes completely in water, so the water will get the H+ there to form high concentration of hydronium ion. So you will always say those 2 parts, to say it must ionize completely in water, and you must as well indicate to form a high concentration of hydronium ion. And we're saying examples of strong acid, HCl, your sulfuric acid, and your nitric acid. When it comes to weak acids, we're saying these ones, they ionize in completely. So the difference there is the in. To say these ones, they won't ionize completely. And then we are saying that in water, then they will form a low concentration of hydronium ion. So we're saying a weak acid will ionize incompletely in water to form low concentration of hydronium ion. So we're saying strong acids, they form high concentration of hydronium ion because they ionize completely. Whereas the weak acids, they will they will form a low concentration of hydrogen ion because they ionize incompletely. And when it comes to bases, we talk about dissociation. And then because the bases they've ionized already, so they dissociate. A base, we are saying it dissociates completely in water to form a high concentration of hydroxide ion. Remember, this is not a hydroxyl ion, then as you did in organic when you were doing the hydroxyl group, the functional group of alcohol. We are saying OH minus is hydroxide ion. So don't make a mistake of saying hydroxyl ion. Example of strong bases are sodium hydroxide, potassium hydroxide. We'll talk about them. The weak bases, we are saying they dissociate incompletely in water to form a low concentration of hydroxide ion. Example of weak bases we are saying is your ammonia, your calcium carbonate, your potassium carbonate, all the carbonates that we are having there, the sodium carbonate, the sodium hydrogen carbonate, as long as the metal and the carbonate, those would be your weak bases. So you don't forget these examples, but I think as we move with the slides, we will be able to give you these examples nicely. Now, we are saying this acid can be concentrated or diluted. Now, I want you to differentiate between a strong acid and a concentrated acid. Learners do have misconception there. I want to remove it to say, remember, when you talk about a strong acid, we're talking about how it will ionize, in water or in aqueous solution. So when you talk about concentrated, we're talking about now the issue of concentration. Remember, you define concentration as C equals to N over V, which is the number of moles of a solute per volume of a solvent there. Now, if you check, we are saying when you say concentrated, we are saying we are having a large number of moles per unit volume, or you can say a large number of moles in proportion to the volume of water. That's how we will define concentrated. So just go to the formula of concentration, which is C equals to N over V. And remind yourself that concentrated means we have a large number of moles per unit volume in proportion to the volume of water. I know you were doing rates of reactions where you talked about when you increase concentration, you increase the number of particles per unit volume. In this case, when we say concentrated, we are saying you have a large number of moles of an acid or a base in proportion to the volume of water. Now, it doesn't mean that if you take a strong acid and you put a lot of water on it, it doesn't make the acid to be weak. Remember, HCl is a strong acid. No matter how much water you can put or you can add on HCl, it will remain a strong acid. But if you add more water on HCl, you are diluting it. You are not changing its strength because it is a strong acid as HCl. Whatever you do to it in terms of addition of water won't change the strength of HCl, but it will change whether it's concentrated or diluted. So the amount of water added doesn't change whether the acid is strong or weak. It changes whether it's concentrated or dilute. So what am I saying? I'm saying now a dilute acid will contain a less number or small number of moles in proportion to the volume of water. So a small number of moles in proportion to the volume of water. So don't forget that to say concentrated is not to be confused with strong and weak. Strong is how much it will ionize when we put it in water. We said strong acid, they ionize completely in water. Weak acid, they ionize completely in water. But concentrated, we're saying the number of moles, how much of the number of moles do we have of the acid in proportion to the volume of water. So when you say concentrated, we're saying it's the large number of moles of a substance or of an acid or a base in proportion to the volume of water. When we say is dilute, it means we have less number of moles in proportion of volume of water. It means we have more water added. When we have less water or no water added, we'll say that is concentrated. I think there's a question that we like to ask to say if we give you 0.1 moles per cubic decimeter, for example, of HCl, is it dilute or concentrated? So you will see that 0.1 is when you have 1 over 10. You will get 0.1. 1 over 10 gives you 0.1. So you are able to see that we have less number of moles in proportion, because the number of moles is 1, the volume of water is 10. So you have less number of moles in proportion to the volume of water. That makes it dilute. So when you see 0.1 moles, less than 1 moles of a substance, you know that that is diluted, because it means we have less number of moles in proportion to the volume of water. I hope you won't confuse the strong and the concentrated, the dilute. You now understand the difference. To say, when you say concentrated, we are referring to the number of moles in proportion to the volume of water. To say, when you say concentrated, we are saying with large number of moles of a substance in proportion to the volume of water. When you say dilute, less number of moles of a substance in proportion to the volume of water. I hope you have that, and then it will help you with when we move with questions. Now, we are saying you are going to talk again about acid-base reactions. So we're going to look at these reactions when acid is reacting with a base. Now we are saying you must be able to write down the reaction equations of aqueous solutions of acids and bases. Examples: if you put, for example, HCl in water, we said it will ionize completely. I just said that to form high concentration of hydronium ion. You can see that we refer to HCl as a monoprotic acid. What does monoprotic acid means? It means it can donate only one proton, because it has only one hydrogen ion. So it's only one hydrogen ion that a HCl can donate. So we call it, or we refer to it as monoprotic. Now, if you look at ammonia, for example, is your base there. When you put it in water, your ammonia to react with water, it will form ammonium ion and the hydroxide ion. So you are able to check that. But if you are having sulfuric acid, you put it in water, it's a diprotic acid, which means it will react with two moles of water there. It will be two of waters that you need there. Hence, you are saying you'll be having sulfuric acid plus 2 moles of water, giving you 2 hydronium ion and the SO4 minus. Remember, these are 2 steps. It means the first step, you'll have H2SO4 reacting with water to form H3O plus HSO4 minus. From there, we go to the second step, where HSO4 minus will react with water to form another H3O plus SO4 2 minus. That's what we're having at the end of the day. So we refer to sulfuric acid as a diprotic acid because it can donate 2 protons, because it has 2 hydrogen ions. So it can donate 2 hydrogen ions. Hence, we refer to it as diprotic. We have other acids like your phosphoric acid, which is H3PO4. So you can say it's a triprotic acid, or you can just say it's a polyprotic acid, because polyprotic acid means it can donate many protons. Many protons. Poly means many. So you got to know this definition to say what is monoprotic, what is diprotic, what is poly, or what is triprotic. So you are able to always remember that. Now, the expectation is that you must be able to identify conjugate acid-base pairs. Conjugate acid-base pairs for given compounds. You must be able to describe a substance that can act as either acid or base. Ampholyte. So you must know an ampholyte. We're saying this one, an ampholyte is an actor, because it can act as an acid or a base in another reaction. So you got to do that. The only thing that I must let you know here is, don't make a mistake of thinking that water is the only ampholyte or is always acting as an ampholyte. You might find that there is water, but it's not an ampholyte in that particular reaction. We know that water can act as an acid or a base, but it doesn't mean that in any reaction you will take water as an ampholyte. There will be situations where water will be acting as a base, not as an acid, or as an acid but not as a base. So water is one example of an ampholyte, but it can act as both the acid or the base. But we are simply saying that not all the time water is our ampholyte. You will see as we go with the lesson that we'll get to understand that. So we are saying you must be able to write a equation to show how an ampholyte substance can act as an acid or a base. So you must be able to do that to show the ampholyte. We'll show you that as we move with our equations. Now we'll deal with neutralization. Remember, neutralization is a reaction of an acid and a base. When an acid reacts with a base to form salt and water. we refer to that reaction as neutralization. So neutralization is the reaction between an acid and a base to form salt and water. So you know that that is neutralization. What I like about neutralization is that these products of neutralization is what we refer to as hydrolysis. Remember, a hydrolysis now is a reaction of salt with water. So reaction of salt with water, we call it hydrolysis. Neutralization is a reaction of an acid with a base to form salt and water. And we're saying the reaction between salt, the reaction of salt with water, we refer to it as hydrolysis. So we're killing two birds with one stone here to say now I've told you what is neutralization, which we are saying is the reaction of an acid with a base to form salt and water. And we are saying the reaction of salt with water, we call it hydrolysis. So have those two concepts. And we are saying the above examples of equations from your exam guideline, you are expected to write this from given information. So we can just in ways tell you that hydrochloric acid react with sodium carbonate to form sodium chloride and water and carbon dioxide without giving you the equation. You must know how to write. So can give you a word equation, you must be able to take it and write it as a form in this equation form. So all these, you are expected to know how to write them. So practice all of those, at least these 6. We're not saying how many, 1, 2, 3, 4, 5. We're saying know them by yourself. And then even when you are given the word equation, you can write it in this form. And then, however, we're saying any other neutralization reaction can be given in the question paper to assess the stoichiometry, for example. So we're not saying in the exam you will only get these 5 equations, but we're saying these 5 is a must that you must know them. So practice and make sure that you know all of them as indicated here in the exam guideline. Now, hydrolysis, already I touched about it when we were doing neutralization. I said to you, neutralization is a reaction of an acid with a base to form salt and water. And I said that salt and water, a reaction of salt with water, we call it hydrolysis, a reaction of salt with water. What I want you to bring to your attention is that when you react a salt, for example, sodium chloride salt, the table salt you are using at home, when you put it, you react it with water, it will definitely ionize. It will ionize, meaning that it will be able to form that sodium plus and chlorine minus. So that's what the salt does. So when you put it inside the water, it will definitely ionize like that. So we'll be looking now at hydrolysis, which is the reaction of salt with water. Will sodium plus react with water? Will chlorine minus react with water? That is what we call hydrolysis. So we're going to look at that to say we are expected at the end of this to be able to determine the approximate pH, whether the pH will be equal to, smaller than, or larger than 7 of salts in salt hydrolysis. So we'll always be looking at that. We'll be looking at the hydrolysis of a salt, of a weak acid, and a strong base. You can see the strong always win. So if you have a strong base and a weak acid, you are expecting that your solution will be more basic or alkaline, will be more basic because you are having strong base reacting with a weak acid. So I'm saying to you, the strong one always win. So if you have a strong base and a weak acid, the solution must be a basic, or the solution must be alkaline, because now you are having a strong base reacting with the weak acid. Always look for that. We are saying the solution will be alkaline because the base is strong there. And you know that the pH of bases is more than 7. Remember, you have your pH meter, that is, you can run from 0 to 7 to 14. And we're saying from 0 to 7 in terms of the pH, 0 to 6,9999, you have acid. At 7, you have neutral. Anything more than 7, you have a base. So you're able to see that if I have a strong base, which is around 14, 13, 12 there, reacting with a weak acid, which is around 7, 6, something there, you'll know that the strong base will always come as a winner. Hence, if you have a strong base and a weak acid, the solution would be basic, meaning it will be alkaline, it will be more than 7. But if you are having a strong acid and a weak base. Remember, strong acid is around pH of 1, 2, and around there, 1, 2, 3 there, just less than 3. You are having strong acids there. You are able to see that a strong acid reacting with a weak base, then definitely the strong one always wins, which means that the solution will be acidic if we have a strong acid reacting with a weak base. I hope you get that. And we are saying that the salt of strong acid with a strong base, strong and strong, does not undergo hydrolysis. So it's very much important that when you do hydrolysis, you always check where this salt is coming from. So we will check if we have a salt called sodium chloride, for example, we'll check where is sodium chloride coming from. You will see that sodium chloride is a salt of sodium hydroxide and hydrochloric acid. We'll talk about that. And then you see that sodium hydroxide is a strong base, hydrochloric acid is a strong acid. So when you react them together, the solution will be neutral there. Hence, we are saying this salt of a strong acid and a strong base does not undergo hydrolysis. You will see when we do the activities. I hope you will enjoy that. And then we are going to talk about neutralization. I talked about it already to say now, when we deal with neutralization, we have to use indicators. Why do we need an indicator? Remember what we said. We said neutralization is a reaction of an acid with a base to form salt and water. That's what we said. The reaction of an acid with a base to form salt and water. And then we're saying now, here, when we're having neutralization, there must be an indicator. An indicator, as the name says, indicator, it indicates when you reach the end point. It means when you reach the end point, it means the indicator will change color. When you reach the end point, immediately when you are titrating an acid with a base, and then the color changes because you will have put the indicator inside, it shows that now we have reached the end point, which means that now the indicator, we're saying, is the point where, the end point is the point where indicator changes color. So when the indicator changes color, we have reached end point. But we have another point which is called equivalence point, which in this case we're saying the point at which the acid has completely reacted with the base, or the base has completely reacted with the acid. So when you reach the end point, it means that now we are saying at that point the indicator will change color, and we are saying then we'll have what is called equivalence point, which means that all the acid has completely reacted with the base. And you are expected to perform stoichiometric calculations based on titrations of a strong acid with a strong base, and a strong acid with a weak base, and a weak acid with a strong base. So we have all those types, and you must be able to do some calculations, including percentage purity. So it's important that you do that as you prepare yourself for your June exams. Ensure that the stoichiometry, you are doing well, empirical formula, percentage purity, all those, you know that you are well versed with them, and then you will do well. Now, lastly, we'll have to look at the pH to say the pH and the pH scale. I've already indicated that the pH scale is from 0 to 14, and we said from 0 to just before 7, we said it's an acid, and from more than 7, just after 7, we have the base up to 14. And then we must be able to calculate the pH values for strong acids and strong base. So we're saying when it comes to calculations of pH, we will only calculate the pH of strong acids and strong bases, only for those. And then for calculating of pH, we use the formula pH equals to minus log hydronium, concentration of hydronium ion. Very much important for you to do that. We will do some of these activities as we move on. And you must be able to define the Kw, ionization constant of water, as the equilibrium constant of the ionization of water, or ion product of water, or the ionization constant of water. So you must be able to know that. And we are saying the Kw is H3O plus multiplied by concentration of OH minus, which is equals to 1 times 10 to the power of minus 14. And then that gives you that happens at 25 degrees Celsius, which is 298 kelvins. And you must explain the auto ionization of water, the reaction of water with itself to form hydronium ion. Hence, we call it auto-ionization, because when you have water reacting with water, then we will call it auto-ionization of water, and then that forms hydronium ion and the hydroxide ion. And we must be able to interpret the Ka value and the Kb value, and we're going to talk about all of this. So you can see we have a lot to talk about, and then we must go straight to it, as those are our objectives for this lesson, and we must ensure that we cover all of them. Now we are saying you must be able to compare strong and weak acids by looking at their pH. Remember, we talked again about the monoprotic acids, which you said your HCl, your nitric acid, your diprotic acid, which in this case will include your sulfuric acid, and then the conductivity. Remember, if the acid is strong, we said it ionizes completely, which means it will have higher conductivity. If it has higher conductivity, it has higher reaction rate. So those are some of the things that we'll look. Now, with no any wasting of time, you have done this in grade 11. You have done this. You know that you said the acid produce hydrogen ion in aqueous solution. Remember, that definition is important. And the base, we said it produces hydroxide ion in aqueous solution. And when it comes to Lori Bronsted, we said an acid is a proton donor and the base is a proton acceptor. So please get all those definitions, then we'll move with no problem. So I felt it's important that we show you the common strong acids, to say these are common strong acids that you must know, which is your HCl, your sulfuric acid, your nitric acid. And I've seen now of late HBr, it comes as well. So it's important that you know that hydrogen bromide as well as your strong acid there. It's important that you have it in mind. So those are your strong acids. When it comes to common weak acid, we have hydrofluoric acid, HF there. We have phosphoric acid. We have sulfurous acid. We have oxalic acid and ethanoic acid. And remember what we said about strong acid. We said they ionize completely in aqueous solution to form a high concentration of hydronium ion. And the weak acid, we said they ionize in completely in aqueous solution to form low concentration of hydronium ion. And then we are saying all organic acids are classified as weak acids. Remember, you have done organic molecules, you're doing your carboxylic acid. So we're saying all carboxylic acids, they are classified as weak acids. Maybe you are asking yourself to say, in terms of carboxylic acid, when we're dealing with physical properties, we said carboxylic acids, we said they have stronger intermolecular forces. We said they have two sides of hydrogen bonding. So we said more energy is required to overcome their intermolecular forces. Those are carboxylic acid. If I must remind you what you have done under organic. What are we saying now? We are saying it's important for you to know that the fact that they have stronger intermolecular forces, hence it's not easy for them to ionize completely. Hence we are saying these are now weak acids, because your strength of the acid depends on how easily you can give or you can ionize or you can produce your hydrogen ion. So it's not easy for these organic acids to produce the hydrogen ion. Hence we are saying they are weak acids. So don't be confused to say under organic molecules, we said these are they have the strongest intermolecular force. Indeed, those strongest intermolecular forces in carboxylic acid, they make them weak. They make them weak acids in terms of how fast can they ionize, how fast can they produce the hydrogen ion. They only incompletely ionize. So the bond is so strong that it's not easy for them now to release the hydrogen ion. Hence, we refer to them as weak acids. I hope that helps you. Now, when it comes to common strong base, we're saying these are the common strong base. You see the group 1 elements in the periodic table, which is your lithium hydroxide, your sodium hydroxide, and your potassium hydroxide. These are your common strong. So these all are group 1 elements, linear. You can see that. But we don't want you to think that there are only three strong bases. No, they cannot be three. There are many others like barium hydroxide, for example, is one that we are seeing in some of the questions that is being asked, calcium hydroxide. So it's important that we make you aware of those that are on papers that we are coming across. Your rubidium hydroxide as well, those are as well your strong bases. So it's important that you know these strong bases. Now, when it comes to weak acids, weak bases, we are saying is your ammonia and your carbonates, your calcium carbonate, your sodium carbonate, sodium hydrogen carbonate. So you see that those are your common weak bases. And we are saying the strong base, we said they dissociate completely in water or in aqueous solution to form high concentration of hydroxide ion. The weak base, we say they dissociates in completely in aqueous solution to form low concentration of hydroxide ion. And we're saying your group 1 hydroxides are strong bases. So that one, in terms of your predictable, you know your group 1 metals. They're not with the exclusion of hydrogen, obviously, because it's not a metal. We're saying your lithium, your sodium, your potassium with hydroxide, they form strong bases. And we are saying these other bases, we take them as being weak bases, but I've shown you other strong bases that you will come across, which is important that you have that knowledge, and we have no problem. Now, let's do this activity just as a baseline to check your understanding. We are simply saying this science that we are doing, we are living with it. It's not a science that is not applicable to our day-to-day life. So it's important that we always reflect as well to say how is this acids and bases affecting or impacting in our lives. So what are we saying? We're saying classify the following as acidic or basic. So I'm hoping you are doing the activity. When you look at number 1 there with water. Water, yes, you're correct. Water must be neutral. So water won't be acidic or basic. It will be neutral. But when you have a soap, you must know that this must be basic. It must be basic. This cleaning material, you see that they have basic nature. So you see that your battery acid, you can see that that must be acidic. Your blood must be basic, just little, just about 7.4 in terms of pH. So it's not a very strong base. It's just close to neutral, but it's basic. Then your chicken soup, the one that you are doing at home, is acidic. Then you have your coffee that is acidic. Your drain cleaner, this will be a very strong base. And then definitely the cleaning agents, as I indicated, will be basic. You have your milk, that will be a very weak acid, around about 6, just close to 7. Then you know that is acidic. Your orange juice must be acidic. Your soda pop, your cold drinks you're drinking, they are acidic. And then you are having your speed and your volume, your vomit. Your speed will be basic. However, when it comes now to your vomit, remember the vomit, we're talking about the stomach there. And you know in the stomach we have your hydrochloric acid, which is a strong acid. So you will definitely categorize the vomit as an acid. I hope that helps you to see that this science that we are doing, it is applicable even in our day-to-day life. It's important that you know the data sheet. Table 2 from your data sheet is the data sheet that you will definitely need when you are dealing with this question. It's very much important that we always remind you, because there will be times when you deal with questions where we'll calculate number of moles. We can use any of those to calculate number of moles. And then when we're dealing with our neutralization, we're going to use the CAVA, we call it Havana equation, so that you always remember it to say, okay, that's what we'll use for our titration. We're going to have that equation now, neutralization equation. And then for calculating of our pH, we have minus log concentration of H3O plus as our formula. So it's important that you know this data sheet and you utilize it, because it's going to help you to answer the question. We talked about the ionization constant of water. There it is given as H3O plus multiplied by OH, concentration of H3O of hydronium ion multiplied by the concentration of the hydroxide ion. And we are saying that is equals to 1 times 10 to the power of minus 14. And we are saying that is at 25 degrees, at room temperature 25 degrees Celsius, which is equivalent to 298 kelvins. Remember, if we change the temperature, it means the kW won't be 1 times 10 to the power of minus 14. So it's important that you have that, because some questions will trick you there where we will change. Maybe we can increase the temperature. Then you know that the Kw won't be 1 times 10 to the power of minus 14 because it's 1.10, 1 times 10 to the power of minus 14 at 25 degrees Celsius. Now, let's do the activity. This one is based on conjugate acids and base pairs. Now, remember a conjugate is a look-alike. It's a look-alike. So we are simply saying now, if you are having HSO4 minus here, is it an acid or a base? Remember, when you at the reactant, on the reactant side, we're having the acid reacting with a base. So we must get an acid and a base on the reactant side, or on the right hand side, there on the product side, we must get a conjugate acid and conjugate base. So all the time on the left, we'll have acid reacting with a base or base reacting with the acid to form a conjugate acid and a conjugate base. So now we look at this equation. And the other thing that I want to emphasize here is that the difference between the acid and its conjugate will be a hydrogen ion. And the difference between a base and its conjugate acid, it must be hydrogen ion. What do I mean? If you look at this one, we have HSO4 minus plus water forming H2SO4 minus plus OH minus. So if we are saying look alike, you can see that HSO4 minus, it will look like H2SO4. The difference there is a hydrogen ion. So you see that one must be an acid, one must be a base. But on the left, we said we have only acid and a base. On the right, we have a conjugate acid and a conjugate base. So what am I saying? I'm saying now when you look at HSO4 minus, you see that is one hydrogen deficient, like it's running short of one hydrogen, but H2SO4 has one H plus extra as compared to this one. So the one with more hydrogen ion is an acid. The one with one hydrogen ion less hydrogen ion would be a base. So in this case, we're saying this is HSO4 minus is a base. H2SO4, we know sulfuric acid is an acid, but because it's on the product side, we're going to call it conjugate acid. So we have a base and its conjugate acid, and the different is a hydrogen ion. I hope you got that correct. And then we're having now water. If HSO4 minus is a base, definitely water would be an acid here. Remember we said water is a good ampholyte, can act as an acid, can act as a base. Here, water is acting as an acid, and then HSO4 is your base. So you're having an acid reacting with a base to form conjugate acid, and if HSO4 minus is a conjugate acid, OH minus will be a conjugate base. You can see water is an acid because it has one hydrogen ion extra compared to OH minus. So you see the difference between the acid and its conjugate base is that the acid has one hydrogen ion extra as compared to its conjugate base. So that's how you will categorize them. And then if you look at number B, you have SO4 2 minus and nitric acid. Nitric acid, you know, is an acid. So you know exactly that nitric acid is an acid, which makes SO4 minus a base. So you look now, HNO3 and NO3 minus. This is a lookalike of HNO3, but it's running short of a hydrogen ion. So we call it a conjugate base. And SO4 minus, we said it's a base that makes HSO4 minus a conjugate acid. So the one that you are referring as an acid would always have an advantage of having more hydrogen ions, an extra hydrogen ion. The last one, we're given HX and water. And then that HX and water, if you look at it, you will have your HX and water forming H3O plus. So you can see that between water and H3O plus, this must be conjugates. Now, H3O plus has an extra hydrogen ion, which makes it a conjugate acid. In fact, I want to say to you, always when you have a hydronium ion or H3O plus, you will know that it will always be our conjugate acid. So this gives it away to say when I see H3O plus, that is my conjugate acid. So if HO3 plus is a conjugate acid, it makes X minus a conjugate base. So you are having conjugate base, you just look now at their look-alike to say H2O will go with H3O plus, which means this one is a base, HX is an acid. Now there is another statement that we made here at the bottom here to say a strong acid as a weak conjugate base. So very much important to say, okay, sulfuric acid we know is a strong acid, which means that this base is a weak base. So it cannot be a strong acid and its conjugate, or a strong base, a weak base. A weak base will form a strong conjugate acid, and vice versa. A strong acid will form a weak conjugate base. So I want you to have that understanding as we indicated there. So you are able to have that information. I hope it helps you. This question is there in the exam. You must be able to answer. The question of an ampholyte, I want you to look at this now. Remember, we said in ampholyte, you can refer to it as an ampholyte. You can refer to it as an amphoteric substance. You can refer to it as an amphiprotic substance. I don't want you in the exam to say, when they say amphoteric, you say, we didn't do amphoteric. I don't know what they are talking about. They are still referring to the ampholyte. So you can say it's an ampholyte, is amphoteric substance or amphiprotic substance. We're still referring to the same substance. And we're saying this is a substance that can act, a good actor. So when it's a good actor, can act as a what? As either an acid or a base. So we're saying this substance can act as an acid or a base. Now, I want you to identify an ampholyte here, or an amphoteric substance, or an amphiprotic substance here. So which one will be your ampholyte? Now, it's easy for you to look at this question and say water, because already we've identified water as an ampholyte. But you must check, because you want to check whether indeed water is acting as an acid in the first direction and a base in another direction. So let's check. We have sulfuric acid is an acid. It's reacting with water. Water is a base, because sulfuric acid is always on the left. We have an acid and a base, and we know sulfuric acid is an acid. So that makes water a base. H3O plus, we said, is always a conjugate acid. That makes HSO4 minus as our conjugate base. Now, when you look at HSO4 minus, HSO4 minus is reacting with water. Now, we want to check. If you check, water has one hydrogen less compared to its conjugate acid, which is now H3O plus, which means water is still acting as the base here. That makes HSO4 minus an acid. So this one will be the conjugate base. You see now, water is not an ampholyte here, because in all these two reactions, water is acting as a base. Now let's look at other actors. Let's look at HSO4 is always acid, it's an acid. But look at HSO4 minus, it's a base here, it's a conjugate base here, but here is an acid. So our ampholyte here is HSO4 minus. So it's important to check, always to first check without concluding that it will always be water. Because like in this case, water is acting as a base in all the two reactions that we're having, but our HSO4 minus is our ampholyte, because it's acting as an acid in one reaction and it's acting as a base on another reaction. I hope that helps you and it equips you now. The auto ionization of water, I've talked about it already, to say at 25 degrees Celsius, we'll have this auto ionization of water, where we said it's a water. Auto ionization of water is, we said, is when two water molecules react together to form hydronium and hydroxide ion. Yeah, you can get that question. I've never seen it before. That says define an autoionization, or describe autoionization of water, or what is autoionization of water. But you got to know that autoionization of water is when two water molecules react together. We're having water liquid plus another water, forming hydronium ion and OH minus. The same way you've written the Kc expression, you can write the Kc, the Kw for this one. Remember, on the Kc expression, we said we include only aqueous solutions and gases. The concentration of water, of pure liquids and solids, we said their concentration remains constant, is 1. So you will know that if I'm to write the Kc, which in this case we call it Kw, because it's the ionization constant of water, you will say concentration of H3O plus multiplied by concentration of OH minus. And then that's what you get. These ones, you won't include them because it's just 1. So you divide by 1 is the same as you don't write it. So you can, that's how we get our Kw to be given like that. And we're saying that Kw is equal to 1 times 10 to the power of minus 14 at 298 kelvins or 825 degrees Celsius. And you see there, we said H2O plus stand for the concentration of hydronium ion, and OH minus stand for concentration of hydroxide ion. And we're saying this auto-ionization of water, Kw, is an endothermic reaction. So please always remember that. And if I'm to show you from first simulation to say, you are able to see that where the 1 times 10 to the power of minus 14 is coming from. So remember we said water is neutral. So obviously you're expecting that when you calculate the pH there, you can get pH of 7, which means the concentration of H3O plus is 1 times 10 to the power of minus 7, which is plus the concentration of OH minus, which is 1 times 10 to the power of minus 7. So you are able to see that the pH of water is 7. It is neutral. So I hope it helps you and you have understanding of the ionization constant of water. You will need it when you do the pH calculations. Now, the acid ionization constant Ka. So we have what is referred to as a Ka value for strong acids. So when remember what we said about strong acid, we said strong acids they ionizes completely. They ionizes completely in water, give a high concentration of hydronium ion. So if we were to do the same to calculate the Ka value or to get the Kc expression here, you know that in this case, because we're talking about the ionization constant of acid, we'll call our Kc there Ka, because this one is specific for the acid, which in this case, you're going to say the concentration of the product, which is the concentration of hydronium ion, and the concentration of the chlorine ion, which is Cl minus there, which is your Cl minus, that will be divided by the HCl, the concentration of HCl. So you are able to see now that now for the Ka value, you are having this reaction ionizing completely, which means we have very little of HCl remaining. Hence, we are saying the Ka value will be big, or will be very large, or will be greater than 1. So immediately when we say Ka value is greater than 1, we are saying this is a strong acid. So Ka value is there to describe the extent of ionization and therefore to give us the strength of an acid. So instead of telling you in the exam that this is a strong acid, we can simply say the Ka value is greater than 1. You got to know that when the Ka value is greater than 1, it means that we are dealing with a strong acid. So I hope you got that. To say Ka value of greater than 1 means it's a strong acid. And then you can see here was just to demonstrate to you that we had the acid reacting with water there. And then you can see that it ionizes completely. You can see we only have the A minus and the H3O plus on that magnified glass there. So you're able to see there that it ionizes completely. We no longer have HA and water remaining. If they remain, there will be very little of HA remaining of the acid that remains, because the acid, it ionizes completely to form H3O plus, which is indicated in brown there, and your sky blue there, which is your A minus. So you're able to see that a strong acid, it ionizes completely, hence you are saying the Ka value will be greater than 1. Now, if we look at a weak acid, the weak acid, it will ionize. I told you about carboxylic acids. Say they are weak acid because they don't want, because of the stronger hydrogen bonds that we talked about. I want you to remember that, to say these ones, they don't want to give away. Hence, you can say this equilibrium lies to the left. What does that mean? It means only few of the of this ethanoic acid will ionize, will form H3. Hence, we are saying a weak acid ionizes in completely to form low concentration of H3O plus. So there is very few of H3O plus formed there. Hence, we are saying Ka value, and then you are saying it will be the concentration of hydronium ion, concentration of the acetate ion there, divided by the concentration of CH3 COH. But because we have this ethanoic acid that did not completely ionize, that very less of it ionized. So it means we are dividing by a very big number here. Hence, we are saying the value of Ka will be less than 0. So when you say Ka value is less than 1, we are simply saying to yourself that this is a weak acid. So Ka value of less than 1 shows you the strength of an acid to say this is a weak acid. So weak acid, they have a Ka value of less than 1, and then strong acid, they have a Ka value of greater than 1. Don't confuse this with concentrated and dilute. Remember, with concentrate, with dilute, I said they will have a 0, something in terms of the dilute acids or base. It will be 0, something because we have a large number of a substance divided in proportion to the volume of water. So in terms of concentrated and dilute, we are looking at the number of moles in proportion to the volume of water. But when it comes to the strength of an acid, whether it's strong or weak, we're looking at the Ka value. And we're saying Ka value of a strong acid is greater than 1. Ka value of a weak acid is less than 1. I hope you are moving with me. When you see a Ka value, you know that we are giving you the strength of an acid. The same applies now here. You will see that only few of these acid, the Ha there, the gray one, you can see that it is only few of it that will ionize. Hence, you see we only have the brown color there, the H2O plus and the sky blue there. You see that it's only few that have ionized because we are saying a weak acid ionizes incompletely. Hence, we are saying that now the Ka value will be less than 1, and Ka value of less than 1 tells you that it's a weak acid. So I hope that will help you. When it comes to the Kb value, the same principle applies here to say for a strong base, Kb value, we won't call it Ka because we're talking about the ionization constant of a base. When it's greater than 1, we are saying it's a strong base. But when it's and then you can see that it ionizes completely. We have no base that remains there. We have the M plus and the OH minus. So you can see that because of it it dissociates completely. Then we are going to say our ionization constant of a base Kb value is greater than 1, and we are saying this is for the strong base. So when we say weak base, it means the Kb value would be less than 1. So when you see the Kb value of less than 1, it tells you that now we are dealing now with a weak base. Why? Because the ammonia will not dissociate completely, meaning that now we have more of ammonia remaining compared to the product there. And so we are dividing a smaller numerator with a bigger denominator, if I must bring your maths there. So you can see that the Kb value of a weak base would be less than 1. So Kb value less than 1, you know weak base. Kb value greater than 1, you know strong base. Ka value greater than 1, you know strong acid. Ka value less than 1, you know weak acid. Please always have that in your mind. Ka and Kb value are giving you the strength and the extent at which the acid and the base dissociates or ionize respectively. Now, with no waste of time, I've already indicated in terms of dilute and concentrated to say when we say concentrated, we are saying we have the large number of moles in proportion to the volume of water. That's why we're saying concentrated, small c there for concentration. So concentrated, we said it's a large number of moles in proportion to the volume of water. And dilute, we said no, this one we have less number of moles in proportion of volume of water. So we have a lot of water that has been added, hence we are saying is diluted. But concentrated, no water or very less water or very little water has been added. So you got to know the definition of concentrated and dilute as we talked about it. I hope that helps you. And then you will remember all this and it will help you as you move forward. Now, if I'm to look at the conductivity and reaction rate, you will see that as long as we are talking about strong acid that ionizes completely, obviously, because we have more ions there, the reactivity will have a high electrical conductivity. Hence, you see the brightness of the light bulb there. For strong acid, when connect it there, you will see that your light bulb will light very nice and then it's very bright. And then in terms of reaction rate, it will have a strong acid has a higher reaction rate. Now, when it comes now to weak acid, you can see the brightness, electrical conductivity is decreases, it's less electrical conductivity, even the reaction rate is less. So you see that even in terms of the light bulb there, just to indicate the electrical conductivity of a strong acid and a weak acid. But when you look at the electrical conductivity and reaction rate of a strong base, because we said it dissociates completely, so it will have higher electrical conductivity, hence you have the brightness there. You can see it's very bright, and then you are able to see that, okay, it means because it ionizes completely with more ions, so we are able now to have a higher electrical conductivity, and we are able to have higher reaction rate. Yes, so I hope that helps you. Even when you prepare for exams, you'll remember that I will have a lower electrical conductivity and reaction rate for weak base because it dissociates completely in water to form low concentration of hydroxide ion. Hope that is good for you. And then, with no wasting of time, let's go now and do problem solving based on hydrolysis. Remember what we defined hydrolysis. We said it's a reaction of salt with I didn't say and. I said the reaction of salt with water. The reaction of salt with water. Now, here are the steps of hydrolysis. So when you're saying hydrolysis, whether a salt will undergo hydrolysis or show the hydrolysis of a particular salt, we are saying follow these steps. They will help you. These steps will be very much helpful to yourself. Now, let's look at it this way. We're given ammonium chloride, NH4Cl. NH4Cl is our salt. Now, the first step that we do, we must be able to split the salt. Remember, when we put the salt in water, I said it ionizes. So the salt will be split. It will be split into NH4 plus and chlorine minus. NH4 plus and chlorine minus, that is our salt. After splitting the salt, we must know where is this salt coming from? Where is these ions that we have just split? Where are they coming from? So it's very much important because the behavior depends on where it's coming from. It's like when somebody's misbehaving, somebody's saying, this child is behaving like this because it's coming from where. So it's important to know where this ion is coming from so that we can understand its behavior. Now, if you look at NH4 plus, you can see that this one must be coming from ammonia, NH3. We know the base, that is NH3, which is a weak base. If you look at HCl, Cl minus is from HCl. We know that the common acid that we're having, the strong one. So this is a strong acid. And what are we saying? We're saying the ions of a strong acid does not undergo hydrolysis, but the ions of a weak base and weak acid, they undergo hydrolysis. So for hydrolysis to occur, the source must be from a weaker acid or a weaker base. So we are simply saying here, ammonium ion is from a weaker base that is called ammonia. It will undergo hydrolysis, which means now the water will react with ammonium plus, not chlorine minus, because chlorine minus is from a strong acid, and we are saying a strong acid does not undergo hydrolysis. I'm happy you are moving with me like that. So no hydrolysis for for ions from strong acid or strong bases. Hydrolysis for ions from weak acid and weak base. So I think ammonium ion NH4 plus is from ammonia, which is a weak base. It will undergo hydrolysis, meaning that the NH4 plus, it is the one that will react with water to form. Remember the H4 plus, it will donate the H plus there to water to form H3O plus and NH3. Remember, when we're doing hydrolysis, we are supposed to conclude to say, is this going to be an acidic solution or basic solution? So the reactions that forms H3O plus, it shows that this salt is an acidic salt. So we're saying this salt is an acidic salt because it forms H3O plus. But if you don't want to say that, you can conclude like this as well. You can say this salt that is called ammonium chloride is formed from a strong acid and a weak base. A strong acid, which is HCl, and a weak base, which is NH3. So the stronger one always wins. So if the strong one is the acid, the salt must be acidic. So you are saying this salt is acidic because it's a salt of a strong acid and a weak base. Or you can say this salt is acidic because it forms hydronium ion. I hope you got that. And then that is the first example that we have done. I hope it will help you as you solve. And I've seen the question papers that we are having these days. Hydrolysis is being assessed, so it's important that you understand this process. Let's do another example. We are given sodium acetate or sodium ethanoate, which is your CH3 COONA, sodium ethanoate. Now, when you have that sodium ethanoate there, remember what steps? The first one, we put it in water, it must be split. It must be split into the cation and the anion, the negative and the positive. So you know you are having your metal, which is sodium plus metal ion, and you are having your acetate, which is CH3COO minus. You're just splitting it like that. And then immediately when you have that, I told you always let's check where are they coming from. Where is the sodium plus coming from? Where is the ethanoate coming from? So definitely you will know that sodium plus is from sodium hydroxide, a very strong base family. Ne? And then you look at ethanoate, you're saying, ethanoate is from ethanoic acid, which is a weak acid. We said it ionizes incompletely. But sodium hydroxide is a strong base. Remember, we said group 1 elements, hydroxide, are very strong bases there. Now, it means now you are going to say this one from a strong family, sodium plus, will not hydrolyze. No hydrolysis. From strong base, no hydrolysis. As long as you're coming from strong family, no hydrolysis. But now this ethanoic acid is from a weak acid. So definitely it will undergo, because it's from weak acid, it will undergo hydrolysis. And remember, it is the ion that undergoes hydrolysis, which means it will be CH3COO minus reacting with water to form ethanoic acid and OH minus or hydroxide ion. Now, very much important here for you now to say this salt will be basic. Why? Because it forms hydroxide ion. So the salt that for the reaction of salt with water that forms hydroxide ion, it shows that the salt is basic because it forms hydroxide ion. The reaction of salt with water that forms hydronium ion is an acidic salt. So now you can conclude that this salt is a basic salt because we had a strong base reacting with the weak acid, the strong winds. Or you will say because OH minus is formed. OH minus, which is a base, is formed. So that is how you will always conclude. I hope you can't wait for the exam to do this type of questions under hydrolysis and collect marks. Now, here's a question. You can think about it. Is the salt potassium hydrogen carbonate KHCO3 acidic or basic? Explain with the aid of a balanced chemical equation. That's how the question will come in your exam to say, no, show us, is this an acidic salt or a basic salt? Now, a science learner who was in this session, enjoying the science session today, will say, I'm given a salt, I'll put it in water, I will split this salt. I'll split this salt into the cation, which is our metal ion, and the HCO3 minus. And then we will check where is the ion coming from. Potassium, you know, is from potassium hydroxide. And then HSO3 minus, you know, is from carbonic acid, which is a weak acid. So we have the weak acid, which is carbonic acid. We have potassium hydroxide, which is a strong base. So you can see the salt must be basic because we said the strong one always wins. So this salt must be basic. But when it comes to hydrolysis, it must be hydrolysis of weak acid. Only the weak undergoes hydrolysis, the weak acid and the weak base. So this one is strong, no hydrolysis this side. It is the ion that undergoes hydrolysis, which means you are going to take your HCO3 minus and then you add it to water. Then you are able to say, okay, this will form H2CO3, which is carbonic acid, plus hydroxide ion. This salt forms hydroxide ion. It shows that this is a basic salt. Or I said you can say this salt is a salt of a weak acid and a strong base. so the salt will be basic. So you are able to get all your marks. I hope hydrolysis you are moving. You can't wait to write about it. Now we're going to look now at titration. Very important procedure here. We're saying now here when you're dealing with titration, it's important that you know that remember we're talking about here you are reacting an acid and a base at the end of the day, and we are saying remember you must know when you reach the end point. We said when you reach the end point, the indicator must change color. So it's important that you know which indicator to use when. When I'm reacting a strong acid and a strong base, what type of indicator will I choose? So that's what we're going to deal with. A color change. What is the color change that I'm looking for when I reach the end point? Because remember we said at the end point is a point where the indicator will change color. So when the indicator changes color, which color? From which color to which color? This is what we're going to talk about, which I'm very passionate about. Remember we talked about the equivalence point, which you said at this point is a point where all the acid or a base has reacted completely with a base or an acid. So you know that equivalence point and end point, two different things. I usually will say you arrive at the end point, but the equivalence point is the event that is happening when you arrive. What do I mean about that? I mean the end point, you are able to see it. You see it by color change that I've reached the end point. But what is happening at the end point? We're saying all the acid has completely reacted with the base, which is what we call equivalence point. So you got to be able to see and not confuse end point with equivalence point. And we're saying we must be able to do the stoichiometric calculations, and you must be able to prepare a standard solution. You must know how to prepare it. What is a standard solution? We're saying a standard solution is a solution of known concentration. So we're saying you will have a solution of known concentration when during this titration, one of the two between the acid and the base, you must know the concentration. Hence, we are saying it's a standard solution. So you must have a standard solution that you are going to use to determine the concentration of the other one that is unknown concentration. And you must be able to know the procedure of how titration is done, and then you must know the precautions and then describe the measures that need to be taken to ensure that reliable results. Remember, when you're doing experiment, we'll expect you now to ensure that you limit errors there, so that at least your results are reliable. And then you must be able to interpret the results and to determine the unknown. Remember, I said for titration, for neutralization equation, which I said is that one governor or CAVA over CB, VB equals to NA over NB. So you know that that is the equation you are going to use now. And then you are going to determine the concentration of either the acid or the base. One of them will be known, and we are referring to that as a what? As a standard solution, because we're saying a standard solution is a solution of known concentration. I hope that helps you. And then these are the apparatus. It's important that you understand these apparatus, because we do ask you questions in the exam that says identify the apparatus. So it's important that you know which apparatus I'm going to use for titration. So we're saying it's a method of determining the concentration of an unknown solution using a solution of known concentration. Already I told you that a solution of known concentration is a standard solution. So we're going to use a standard solution to determine the concentration of another solution. Now, we call this volumetric analysis. We use the beaker. You can see we have the beaker, we have the volumetric flask, we have the conical flask, we have the burette, very popular, the burette, where we can have the funnel, we can have the wash bottle, we can have the pipette. And you can see, and then we use what is called the rotate stand, so that we can hold everything nicely before we do our titration. And then you can see that in the conical flask, you can call it conical flask. Sometimes we refer to it as Erlenmeyer flask. So in our Erlenmeyer flask, we can have our acid, and then we have our acid And then in the burette there, Q, which is our burette there, we can have our sodium hydroxide solution. Remember, we're saying one of the two, either the base or the acid. We know the concentration. Hence, we call that a standard solution. That must be prepared before we start with the reaction. So the main aim is that between the acid and the base, you have one of them is a standard solution, or you know the concentration of one of them. I hope that helps you. And then that's how you would set up your apparatus. Now let's look at the experimental procedure given to you here, simplified. Now you can see step number one. We're saying we're going to use the pipette. We're going to use the pipette. Here's the pipette, step number one here. We're going to pipette a standard solution, which is the solution of known concentration, into the conical flask. So we do that, standard solution into the conical flask. And then we're going to add an appropriate indicator. Remember what the indicator does. We said it will show us when we reach the end point, because the indicator will change color at the end point. And then we'll have our equivalence point, which you said the equivalence point is the point where all the acid or the base has completely reacted with the base or the acid. And then step number one, we prepared the acid solution into the flask. Step number two, we added the indicator so that it can show us when we've reached the end point. Step number three, now we're saying now add a solution of unknown concentration to the burette. So we're having a burette there. A burette, remember, we are knowing the concentration of the acid, so the unknown one is in the base here, which is in the burette. We add that, and then we're saying place the conical flask under the burette. So that's your fourth step. You've placed them like that. And then we are saying now add the solution from the burette to the conical flask, one drop at a time. So we don't want you to just open your flask like that, your burette like that, and then because you might pass the end point. So the color change you must be very accurate, that immediately when the color change, you stop the titration. So hence we're saying go drop by drop. And then we're saying swell the conical flask. So step number 6 there, you swell. We didn't say shake, because when you are dealing with chemicals here, you might pour yourself with them. So we're saying nicely swell them nicely. And then we're saying as well, rinse the walls of the conical flask. And we're saying now you close the burette when the solution changes color. So immediately when the color changes, you stop. You can see the color has changed there. Then you stop there. Then you take the initial reading on the burette and then read the amount of solution used. So you are going now to check to say, okay, when we started the burette, we were here. When we end, we were here. Then you're checking the difference there to say how much of the base was used to titrate the acid. So you will have seen when you started, you knew the concentration of the acid, you knew the volume of the acid that you had in this flask, and then when you started again, you will know now the volume of the base that you have used. You don't know the concentration. You don't know the concentration of the base, because that's what you are looking for. So you're going to calculate the concentration of the base. You know the Ca, which is your standard solution. You know the volume of the acid that you have used. You know the volume of the base that have been used from the burette. You are looking for this one. And you know your mole ratio. Remember your Na over Nb. That is your number of moles of the acid over the number of moles of base. So hence we are saying CaVa over CbVb, and that is able to give you that. I hope that helps you and you will understand titration. And then I want to emphasize as well the choice of the indicator and the color change in this slide. To say indicators and color changes, we are saying an indicator is a substance that helps to determine whether a substance is acidic, basic, or neutral. Now, what is going to happen is that if the solution is acidic, we talked about that when we're dealing with hydrolysis. We said acidic solution is when we have a strong acid and a weak base. So when we have a strong acid and a weak base, we're going to use methyl orange. When we are having a strong acid and a strong base, strong, we're going to have neutral solution, hence we'll use bromothymol blue. When we are having weak acid and a strong base, we're going to have a basic solution, as we did during hydrolysis, and the indicator we'll use is phenolphthalein. Now, if we're using methyl orange here, we're expecting the color to change from red to orange. If we are using bromothermal blue for neutral solution, the color will change from yellow to blue. If we are using phenolphthalein, remember the pH is silent there. So it's phenolphthalein, the pH is silent. Now the color change will be colorless to pink. What am I saying? I'm saying you put them, you arrange them in this way to say we have acidic, neutral, and basic. Acidic is for strong acid and a weak base. Neutral is from strong acid and strong base. Basic is from, or alkaline is from a weak acid and a strong base. So you know. Now we said MBP so that you don't forget. MBP. The M is for methyl orange. You use it for acidic solution. Bromothiamine blue, you use it for your neutral solution. And phenolphthalein, you use it for your basic or alkaline solution. And when it comes to colors, nicely simplified for you here, we said Roy B. Cap. Roy B. Cap. What are we saying? We're saying the color change when you're using your methyl orange for strong acid and the weak base, it will be from red to orange. The color change for your neutral solution when you're using bromothiamine blue will be from yellow to blue. The color change when you're using your weak acid for weak acid and strong base, when you're using your phenolphthalein, the color change will be colorless to pink. Please always remember that, and then you will do well when it comes to questions involving this type of questions. Now, pH, when it comes to pH, remember we are saying the pH scale is from 0 to 14, and we said we only calculate the pH of strong acids and strong base. So we don't calculate the pH of weak acids and weak. So we won't be saying calculate the pH of phosphoric acid, for example, H3PO4 is a weak acid. So we won't ask you to calculate its pH. We'll only ask you to calculate the pH of strong acids and strong base. Hence, it's important to know the strong acids and strong base, which will indicate that is your HCl, it's your nitric acid, is your sulfuric acid. I added as well your hydrogen bromide, HBr, as well as your strong acid. So you got to know those as your strong acid. When it comes to strong bases, we have said is your group 1 elements hydroxide, which is your lithium hydroxide, sodium hydroxide, and potassium hydroxide. I've included to say barium hydroxide, rubidium hydroxide, calcium hydroxide, so that you have almost all of these strong bases that you are expecting. And when we calculate the pH, we are saying we use minus log concentration of hydronium ion. So you can see the base does not have hydrogen ion, hence you will need the ionization constant of water so that you are able to calculate the concentration of H3O plus first before anything. There's a minus there. So it's important that you have that. We talked about all this. So we're going to look now at examples and activities so that we can do this type of questions. Now, look at this question taken from a previous question paper. I think it's 2019. Yeah, November 2019. Define a base in terms of Arrhenius theory. Define a base in terms of Arrhenius theory. So you get this type of questions for 2 marks. Define a base in terms of Arrhenius theory. So it's very much important for you now to say, okay, a base, but you must check in terms of who. Because if you make a mistake, you say a base is a proton acceptor, you are wrong because that is Lowry-Bronsted. So it's important that you check, is it Arrhenius? Is it what? Remember, with Lowry-Bronsted, we said just 2 ways are important: proton, donor, proton, acceptor. But when it comes to this, we said 5, which in this case, we are saying a base produce, according to Arrhenius, a base produce hydroxide ion, OH minus, in aqueous solution. In aqueous solution. So you are able to get your 2 marks. That's 1, 2, 3, 4, 5. Wait. Produce hydroxide ion in aqueous solution. You got your 2 marks with you. Please get these marks and collect them. Explain how a weak base differs from a strong base. So it's important that you don't forget. Remember, with bases, we talk about dissociation. To say a weak base will dissociate incompletely in aqueous solution or in water to form low concentration of OH minus. So this one, weak base, it will dissociate. We agree? It will dissociate, but it will dissociate incompletely. In what? in water to form what? To form low concentration of hydroxide ion. But when it comes to a strong base, it will dissociate completely. So all of them, they dissociate, but the weak one dissociates incompletely. The strong one will dissociate completely. It will dissociate completely in what? In water to form high concentration in water or an aqueous solution to form high concentration of hydronium ion. So this one forms high concentration of hydronium ion. So you are able to get your 2 marks there. Remember, your 4 marks richer. You are moving in the right direction. And then we are saying write down the balance equation for the hydrolysis of sodium hydrogen carbonate, NaHCO3. Remember the steps for hydrolysis with 3 marks. So please collect these marks as much as possible. Remember the steps. You said you put it in water, you split the salt. The salt will be split into sodium plus and HCO3 minus. Then you look where they come from. You say sodium plus is from sodium hydroxide. Sodium hydroxide is a strong base. So for strong families, said no hydrolysis. Unfortunately, sodium plus will not undergo hydrolysis. HCO3, it comes from carbonic acid, H2CO3. And then we said this is a weak acid. A weak acid will undergo hydrolysis, which means now the ion that will undergo hydrolysis is HCO3 minus. So you are simply going to say HCO3 minus plus water gives us H2CO3 plus OH minus. Your conclusion, the salt will be basic. Why are you saying the salt is basic? It is basic because it produces hydroxide ion. It produces hydroxide ion, So this is a basic salt. Or because it's a salt of a weak acid and a strong base. Then you go to 3 marks, you are richer. You are looking forward to other questions and to move. Now, yes, we have a real question now. A real question is coming. He's saying Elena wishes to identify element X in the hydrogen carbonate. So you can see we're having X here. So we don't know what metal or what substance is that one. So the learner now has to identify that metal or that substance. To do this, she dissolves 0.4 grams of XHCO3 in 100 ml of water. She then titrates all the solution with 0.2 moles per cubic decimeter hydrochloric acid solution. Methyl orange is used. I know you understand. Methyl orange. Then you know that this one must be a strong acid and a weak acid. Remember we said acidic. You will use methyl orange. We've been talking about the color change, Roy Bicap. We said for methyl orange, it will be from red to orange. You see the importance of understanding now all these types of titration and the indicators and the color changes as well. So you will be able to tell us if we ask you what will be the color change. If we ask you why we're using methyl orange, you'll say it's because we're titrating a strong acid and a weak base. Now calculate the pH of the hydrochloric acid solution. The pH, you know now, you will say P. The P is small letter there. The H is capital. So please make sure that you don't write pH two equal ways like that. Just copy it the way it appears in the data sheet. It will help you because it will penalize you if you just write pH as 2 like that, equal like that. No, you must copy it correctly and then write the formula as is given. Then you're able to say minus log. Now you know that if you have ACl in water, it will definitely form H3O plus and Cl minus. And you see that the ratio between HCl and H3O plus is 1:1. Hence, you will put the concentration of the HCl is equal to the concentration of the H3O plus. So you will just take 0.2 and put it there and take your nice calculator. And I advise you that if you have a particular calculator, you are using it, use the same calculator throughout the year so that you don't have problems of changing calculators during exams. Now you won't be sure of your answer. And then you are able to say minus log 0,2. If your calculator is working well, you'll got 0,6989. You can round it off to 0,70. And that is correct. And then remember, the SI unit of pH is nothing. You don't write the SI unit there. You just write it as 0,70. Now, okay, 2.4.2, give a reason why methyl orange is a suitable indicator. I think I've indicated to you that. So, okay, this one is because it's a reaction of a salt, of a strong acid, and a weak base. Or you will say because it's a titration of, this is an acidic solution, and for this acidic solution we need methyl orange. Remember what we said? We said it's acidic, it's neutral, is alkaline or basic, A and B. For acidic we said it's methyl orange, and then for neutral we said it's bromothymol blue. For basic or alkaline we said it's phenolphthalein, MBP, so that you always remember that and you have no problem. The color change we said is Roy B cap is from red to orange, from yellow to blue, from colorless to pink. So whichever comes in the exam, you know you are comfortable. Now let's answer that question. It says give a reason why methyl orange is a suitable indicator. We said because this is the titration of a strong acid with a weak base, or because the solution is acidic, then we need a methyl orange as an indicator there. It is suitable. Now at the end point, she finds that there is 20 mils of the acid neutralized all the hydrogen carbonate solution. The balance equation for the reaction is given as X HCO3 plus HCl, XCl plus CO2 plus water. Identify element X by means of a calculation. You see, here you must be richer if you do this calculation correctly. Now, we always say it is important that you always start from what you know. You move from what you know to what you don't know. For example, you have seen that you had 0,2 moles of per cubic decimeter of hydrochloric acid, and then at the end point you had 20 mils of the acid that neutralized all the hydrogen carbonate. So you can see that for this one, for HCl, you have C equals to N over V, which in this case the C was 0,2, and then you have your N over V. The volume that was used was 20 cubic centimeter. In real sense, I find it much easier to work with the neutralization equation, where you will just use the Kavanaugh equation, CAVA over CBVB equals to NA over NB. It makes matters even good, because when you're using this equation, we don't even expect you to convert your 20 cubic centimeters and your 100 cubic centimeters. You just use them as they are. Then it makes it much easier, and you're able to collect your marks even much faster. Then if you're using that equation, you will have seen that the concentration of the acid was 0,2. The volume of the acid was 20 mils, so it's 0,2 times 20 over the concentration of the base is what we are looking for. But the volume of the base we're given, it was 100 mils. It was dissolved in 100 mils of water, so that is 100 there equals to. And if you look at the equation, is 1:1. The mole ratio is 1/1. So you just do like that, and you take your calculator, you multiply 0,2 times 20 equals to 4 equals to that, and then you are able to cross multiply, and then you are able to say, okay, now I must divide by 100, and then you are able to get your answer, which is 0,04, which is your C, the concentration of your base there as 0,04. So immediately when you have that, remember it's in moles per cubic decimeter. So once you have that, and then you wanted to identify the mass there, the molar mass of that, which in that case, you know that, okay, already you are having, the concentration is mass over molar mass times volume, and then that is going to help you now in terms of finding out. But what is even much important here is that now you know the concentration of this XHCO3, you know its concentration, and then the main thing that you are looking for now is to find out now what is the molar mass of the entire of it. But what you already know is that you are having H, which is 1, you are having carbon, that is 12, you are having 48, which is 16 times 3 for oxygen there. Then that will give you your 61. So you are able to know that you just want the X part, but you are having your mass there as X plus 61. And then if you to use that information correctly with correct substitution, you are able to determine that your K will be your 39 grams per mole, which in this case will be your potassium. And then you will have got that this is your potassium that you got. So I hope that will help you as we deal with questions as this one, and you will be able to move forward. Now, as I conclude, I will give you a homework that you will do at your own time to say, according to the balance equation below, a dilute solution of HCl is titrated against an ammonia solution, and then you can just take a picture of the questions. You will do them at your own time, and then you will be able to practice and see what you have understood and what you don't understand. Maybe if I go back one page so that you are able to have that for your homework. And then we move now as well to the next page so that you can copy this one as well. So we're saying go at your own time, do this this activity. Let me take it. You can take the picture, you can have it with you so that you can do the practice of the question. And then lastly, we are saying summary as we conclude to say you will remember now that we have done Arena's model, where we said is acid produce hydrogen ion in aqueous solution and the base produce hydroxide ion in aqueous solution. We talked about the conjugate acid-base pairs, knowing that by now you know the difference between the acid and its conjugate base. We said it's a hydrogen ion. We have talked about the pH scale and the pH calculations. We have talked about Lowry-Bronsted, proton donor for the acid, proton acceptor for the base. We have talked about the strong acid and the strong base, where we said that a strong acid, it ionizes completely in water and to produce high concentration of H3O plus, and a strong base dissociates completely in water to produce or to form high concentration of hydroxide ion. We had the weak acid that ionizes in completely, while a weak base, we said it dissociates in completely and it forms the low concentration of hydronium ion. We talked about the concentrated acid, concentrated base, where we said concentrated simply means that large number of moles in proportion to the volume of water, whereas dilute means less number of moles in proportion to the volume of water. So you are able to do that. We talked about the titration, where you use your Gavana equation, the CAVA over CBVB equals to NA over NB. We did all this. We have done hydrolysis of salt. You have seen that the ions of the strong acid and strong base does not hydrolyze. Only the ions of weak acids and weak bases are able to ionize. And then we see preview of the next lesson. This is what we are saying. We are saying just in time on the 23rd of May 2025 at 2:30 to 4 o'clock. We'll be doing electrostatics as you prepare for your exams. And with those words, I would like to say thank you. I close with the words of Albert Einstein, who says, anyone who has never made a mistake has never tried anything new. So keep on trying, make those mistakes, make them fast, don't make them in the exam, make them during practice, and ask as many questions as possible. Thank you very much. Till we meet again.